Yo, what's up everyone? Welcome to Equilibrium Part 2. Today we're going to go over like a bunch of these equilibrium constants, so Kc, Kp, Ksp, Kw, Ka, Kb, etc. Let's start with a review of what the equilibrium constant is. Remember, it's just a general description of the equilibrium condition. And all of these equilibrium constants are just going to follow this basic general form, where K equals the concentrations of the products over the concentration of the reactants. And we're going to go over a lot of these different constants, but essentially they're all based on this little formula, and they're just used in different scenarios. And that's why we give them different names so that it's easier for us to use them. So the most basic one is if you have a equation or like a formula that goes A plus B is in equilibrium with C plus D, your K value or your Kc value would be like this. And Kc just represents that it's going to be, in terms of the concentration, those little brackets around your reactants and your products imply the reactants. And remember, heterogeneous equilibria, these are going to be equilibria involving multiple phases. And in heterogeneous equilibria, you might have something like where 2A is a gas, and it's reacting with 3B, which is a solid. And it's in equilibrium with an aqueous and a liquid. And the important thing about heterogeneous equilibria is that pure solids and liquids are not going to count in the equilibrium constant. So in this case, the Kc would be the concentration of C over the concentration of A squared. So let's take a look at all the equilibrium constants that we're going to use. So we're going to have Kc, Kp, Ksp, Kw, Ka and pKa, and then Kb and then pKb. Let's start with Kc, which, I mean, we've gone over already, but if you have an equation that goes A plus B is in equilibrium with C plus D, this is just going to be your equilibrium constant. And again, these are going to be products over reactants. This general form is going to apply to all these equilibrium constants, so you really need to know this form. Let's go to the next one, Kp, which is going to be the equilibrium constant using the partial pressures. And so it's going to look something like this, where instead of the concentrations this time, we're going to have the partial pressures. And so the Px is going to be the partial pressure of x, and then Kp is going to be the equilibrium constant using these partial pressures. There is a relationship between Kc and Kp, and it's going to be this. So Kp is going to equal Kc times R times T to the delta N. And delta N just it just represents this little value here, where C is this stoichiometric coefficient, D is that stoichiometric coefficient, A is that stoichiometric coefficient, and B is that. Alright, so Kc and Kp are pretty basic. Let's move on to Ksp, which is going to be the solubility product constant. So remember back to our solubility general forms, where you might have a solid that dissociates completely, and you might have a solid that doesn't dissociate at all. And we talk about this quantitatively. We say it dissociates entirely and it doesn't dissociate at all, but really those general descriptions are wrong. And that's because even the solids that don't dissociate at all, or supposedly don't dissociate at all, are going to dissociate to a certain amount. And the way we show how much it dissociates is using the Ksp, or the solubility product constant. So for a general form where A is a solid and it's in equilibrium with B and C, your Ksp is going to look like this. And remember, A is not in there because it's in the solid form, and solids are not included in our equilibrium constant. This form right here is going to represent how much of the solid is going to dissociate. And let's take a look at like a problem using this. So barium fluoride has Ksp of 1.8 times 10 to the negative 7th. What is the maximum fluoride ion concentration possible in a solution with barium, the concentration of barium being 5.0 times 10 to the negative 4 molar? So barium fluoride is going to be BaF2. And if we dissociate that, that's going to be barium and 2 fluorides. So our Ksp is going to be the concentration of barium 2 plus to the first power and the concentration of F minus to the second power. Because remember, the stoichiometric coefficient of the F is the 2. If we're trying to find the maximum fluoride ion concentration, we are going to need to plug in the concentration of not only our Ksp, but our concentration of barium. So 1.8 times 10 to the negative 7th is our Ksp. And the concentration of barium is 5.0 times 10 to the minus 4th. And then we have the concentration of fluoride squared. If we solve for the concentration of fluoride, we're going to get that it's about 1.9 times 10 to the minus 2 molar. And that's going to be answer choice D, which is the right answer. So again, we can use the KSP to find a concentration of a reactant or product if we're given like some other information. Let's do one more. The KSP of SrOH2 is 2.0 times 10 to the minus third. What is the pH of a saturated solution of SrOH2? Saturated just means that all the amount that can dissociate has dissociated. So we have SrOH, and that's going to be in equilibrium with Sr2 plus and then 2OH minus ions. What's our strategy going to be in order to find the pH? Remember, pH is going to be the negative log of the concentration of H plus ions. But in this case, we are not given H plus ions. Instead, we're given OH minus ions. So we have to use POH. POH is going to be the negative log of the concentration of OH minus ions. And we can use this relationship where pH plus POH equals 14 to figure out what the pH is. Now, we know that KSP is going to equal the concentration of Sr2 plus times the concentration of OH minus squared. And what we can do with that is that we can just substitute values for the amount that dissociates. So we can say that the amount of Sr2 plus that dissociates is just going to be S. And if that is S, well, the amount of OH that's going to dissociate is going to be 2S. But remember, this 2S value is squared. So essentially, we have that KSP is going to equal 4S cubed. And S is just going to represent this placeholder for whatever value of Sr2 plus is going to dissociate. Since we know KSP is 2.0 times 10 to the minus third, we can set that equal to 4S cubed and solve for S. S is going to come out to about 0.079. And we can use this value of S to relate that to the concentration of OH. We found that the concentration of OH is going to be 2S. So if we multiply this value by 2, we're going to get that the concentration of OH is going to be 0.159. And we can use this to find the POH. Remember, POH is the negative log of the concentration of OH. So POH is going to be about 0.80. And now we can use this relationship where pH plus POH equals 14 to say that our pH is going to be 13.20, which is answer choice D. And that is correct. This step right here, where we relate the concentrations to the KSP value, is probably the most important part of this problem. If you were able to make this connection, then everything else becomes really easy. But there's also another way to do it, and it introduces something that's going to be really important for all of equilibrium. Let me introduce something known as an ice chart. And an ice chart is where you have all your reactants in your products, and essentially you find the initial, the change in concentration, and the equilibrium concentration. And so let's see what that looks like. Initially, we're going to have some amount of SrOH2. The thing about ice charts is that if we're dealing with something that is a solid, and in this case we know that SrOH2 is a solid since we're being asked to find the KSP, for initial it does not really matter, so we just write down solid. But for the products, we know that those are going to be included in our equilibrium constant, so we need to find their real values. And initially they're going to be 0, right? If you have all reactants initially, then you're not going to have any products. That's pretty obvious. And so our change in concentration, well, we can just say that's negative X. And SrOH2 is going to decrease in that value because the reactants get used up and products are produced. So the amount of Sr2 plus that's produced is going to be plus X. And though the OH is going to be plus 2X. Because remember, we have a stoichiometric coefficient of 2 in front of the OH. So our equilibrium concentration, well, for SrOH2, it's still a solid, so we just say less solid. We don't really need to worry about the actual concentration of the solid reactants in these products. But for the ones that are going to count in the equilibrium constant, we write down the actual value. So plus X and then plus 2X. Now let's write down our KSP again. So our KSP is going to equal the concentration of Sr2 plus times the concentration of OH minus squared. And so we just found out what these are going to be. These are going to be Sr2 plus, the concentration of it is going to be X, and the concentration of OH minus is going to be 2X. So we can plug these back in. So X times 2X squared. And this is just the same as how we just found how we did S in the previous method. And so essentially it's back to the same thing again, where you solve for X and then you relate that to OH, and then you relate that to POH, and then you relate that to pH. So this is a very similar way to do it, but you'll notice that ice charts are a bit more versatile when it comes to other types of problems, not just KSP. So let's move on to KW. And so I want you to look at this really important equation here, where two waters react and they produce H3 plus ions and OH minus ions. This is known as the autoionization of water. And you can see here that the water here is going to act as a base, and the water here is going to act as an acid. I guess you could switch them around, but essentially this one right here, this is going to be the conjugate acid, and this one right here is the conjugate base. Now you see something interesting, and that's that the same compound is both a base and an acid. And this is because water is amphoteric. And for a substance to be amphoteric, it needs to be usable as a base and an acid. So if we were to write our equilibrium expression for this equation here, it would look something like this. And this little thing right here is just what we call Kw. So it's any ordinary equilibrium constant, but we just say it's Kw because it represents the autoionization of water. Now Kw has a specific value at 25 degrees Celsius. At 25 degrees Celsius, Kw is going to equal 1 times 10 to the negative 14th. And this is actually really important, and it'll come up a lot in certain other problems. And essentially another property that piggybacks off of this is acidity. So if you have the concentration of H3 plus ions being greater than 10 to the negative 7th, it's going to be acidic. If it's equal to 10 to the negative 7th, it's going to be neutral. And if it's less than 10 to the negative 7th, it's going to be basic. Let's move on to Ka and pKa. So let's say you have some acid, HA, and it's reacting with water to produce hydronium and A minus ions. If we wrote the equilibrium expression for this, it would look something like this. And that is what we call Ka. And Ka is really important because the smaller the Ka value, the weaker the acid. And so the reverse, the higher the Ka value, the stronger the acid. pKa is simply the negative log of Ka. It's very similar to your pH formulas and your pOH formulas. And essentially, it's going to go like the smaller your Ka value, or the smaller your pKa value, the more acidic, and the greater your pKa value, the less acidic. So something like hydrochloric acid has like a pKa value of, I think, around -8. And then methane has a really high pKa value, and it's going to be a lot less acidic than something like hydrochloric acid. Kb is going to be essentially the same except for bases. So if you have A minus reacting with H3 plus to produce HA and OH minus, you're going to have a Kb expression. And it's going to look something like this. Remember, the water is not added because it's a pure liquid, and liquids are not included in our equilibrium constant. Again, the smaller your Kb value, the weaker the base, but pKb is going to be the negative log of Kb. And it's going to work the same way. So the smaller your pKb value is, the more basic, and the higher your pKb value is, the less basic it's going to be. Let's do a problem with what we did on the last two slides. So a 0.12 molar solution of monoprotic acid is 2.3% ionized. What is the Ka of the acid? Monoprotic just means that there's just going to be one hydrogen. So it's going to have a general formula of Ha. So we say that HA is going to be in equilibrium with H plus and then A minus. And we're told that, first of all, it's a 0.12 molar solution, and that 2.3% of it is going to be ionized. So 2.3% is going to be in the hydrogen, and 2.3% is going to be in the A minus. So how much is 2.3% of 0.12? Well, we can just multiply 0.12 times 0.023, and that's going to be about 0.028-ish. And that represents the concentration of H plus and the concentration of A minus. So our Ka value, remember Ka is just going to be the concentration of A minus times the concentration of H plus over the concentration of our acid itself. So our equilibrium concentration for A minus and H plus, we just found that out. That's going to be 0.028. And since they're both 0.028, let's just say it's squared. And our equilibrium concentration of HA is just going to be 0.12 minus 0.028. Because remember, that amount gets ionized, so it gets converted into your products. And if you solve this, you're going to get that your Ka value is going to be 6.5 times 10 to the negative fifth, which is answer choice C, and that is the right answer. Alright, that's all I have. I hope you learned something about the equilibrium constants and like how we name them differently based on what scenarios are used. Thank you for watching, and I hope to see you next time.